start now. So this is another session of the ESC Ph.D. colloquium talk. We will have 3 talks today, each about 20 minutes. So the speakers are requested to keep the talk within maybe 17 or 18 minutes so that we can have another 3 or 4 minutes of Q&A session. So we start. The first speaker today is Asif Altaf Shah. He is a Ph.D. student here at the Department of Electronic Systems and Engineering. Yeah, I have his bio. So his research focuses on investigating the physics of non-volatile resistive switching into the transition metal dichalcogenic material for next generation memory and neuromorphic computing applications. In addition, he actively collaborates with IMEC Belgium to study the atomistic scale reliability of advanced ruthenium nanointerconnects for the transition from copper to ruthenium in back end of the line for angstrom node semiconductor technologies. Okay, so let's welcome Asif.
Hello everyone, good evening. I'm Asif Altaf Shah. I'm a PhD student in Professor Srivastava's lab. So today I'll be giving a talk on unveiling the interfacial behavior of AU contacted MoS2 atomristors and the role of point defects. So the outline of my talk will be introduction and motivation, and followed by the role of point defects, and then I will conclude. So modern processors such as Core i9 have multiple components of like GPU and CPUs, and at the heart of these components sits a transistor. So transistor is basically a device which turns on and off with the help of a gate. We apply voltage across the terminals, source and drain, and this transistor basically switches billions of times per second, and which enables us to do computations and heavy workflows, AI and other things. So over the years, the architecture of the transistor has evolved from planar FET to currently what we have, gate all-around FET, with the goal to basically have high performance, high speed, and in reducing the energy consumption. But even today, with all these developments and even the state-of-the-art AI, such as ChatGPT, we see it consumes a lot of energy. For instance, a study by Business Energy UK showed that ChatGPT consumes 14 billion kilowatt hour per year. Well, if we see brain, which basically does better cognitive tasks or comparable, it consumes only 175 kilowatt hour per year with an assumption of 20 watts per power. So you see there is a 9 order almost gap between the two. So the goal is to basically compute as efficiently as the brain. So with that in motivation, we have to then develop a hardware which works basically similar to that of a brain. But before that, we need to see where the problem lies. So the current modern computing systems basically have what we call the von Neumann architecture. So in the von Neumann architecture, what we have is we have a processor and we have a memory. And the data constantly shuttles between the memory and the CPU. So the memory sends the data out to CPU, it crunches the data, sends back to memory. And because of this constant data shuttling, we have a lot of energy consumption. But on the other hand, if we see brain, so the smallest unit of brain is what we call these synapses and neurons, which basically do most of the computations. So in brain, what we have is, I show here a simple example. So we have a presynaptic neuron and we have a postsynaptic neuron, and in between we have what we call the synaptic, we have a synapse. So the way it works is basically a signal is sent out from a presynaptic neuron, which travels across the synaptic cleft and then is caught by the neuroreceptors into the postsynaptic neuron. Now, what we have is So for instance, if you take a look at the initial state, so if you have a neuron, so what happens is basically the presynaptic neuron fires a potential across the synaptic cleft, and then it's caught by the neuroreceptor in the postsynaptic neuron. And if an activity is continuously repeated again and again, so what happens is basically now depending on how efficiently the neuroreceptors catch the signal, so you will have a better catch in the postsynaptic neuron. So okay, so what we then have is, so for the same input, what you can see below there, the graph, so you can have multiple outputs depending on what is the strength of the neuron at the synaptic cleft. So you can have either a better signal in the postsynaptic neuron, or you can have a poor signal. So the idea is that for same input you have no multiple outputs. Now to mimic the same behavior into an electronic device, we have what we call a memristor. So memristor basically is a vertical configuration of a device. So it's like a very, very simple device, like you have metal, oxide, and then you have again metal. So initially it is basically, since there's oxide, so the current is very low. So we call such a state as high resistance state, because there is very, very low current. But once you provide a field which is above critical field, what happens is this metal basically migrates through the oxide and forms filaments with between the two metals, and because of it now you have high current, because now we have a conducting path. So this represents the low resistance state. So now you have two states. So a typical characteristics is something that looks like this. So this is experimental characteristics. So again, you see for the same input, now you can have multiple outputs. One you can call as the high resistance state, and the other one you can call low. So this then you can correlate with how transistor works, like you have 0 and 1s. So you can call one state as 0 and one as 1, and that's how you can do computations, you know. Now, over the, like I said, the eventual goal is basically to compute as efficiently as the brain. So one key strategy to reduce the power consumption is scaling. So over the years, like efforts have been made to reduce the oxide in between, okay? So, but it has been observed that reducing the oxide beyond few nanometers cause basically tunneling to cause tunneling currents to move through this device. And because of that, what happens is the high resistance and the low resistance states, the distinction between them gets blurred. And if the distinction between two gets blurred, then it will be difficult to understand which state is 0 and which state is 1. Until recently in 2017, although it has been a decade now, so people discovered that if you put a monolayer of 2D material, which is just 3 atoms thick, in between these metals, they also have a resistive behavior like this. The hysteresis will be seen there. But since up till now, the physics of these devices is not well understood. So so the ongoing studies are going. So that's where basically I picked up my PhD topic, and today we will talk about the role of point defects in these atomristors. So the term atomristor is basically inherited from the memristor, with just the atom here says that since it's 3 atoms thick and it's just monolayer, so we call it atomristor. So here is a typical configuration, as you can see, and this is the experimental characteristics. So again, you see we have their hysteresis. We have 2 distinguishable states, 1 and 0. So in this work, what I did is basically to understand the role of point defects, because you see in these devices, understanding the interface is very, because it's very just 3 atoms thick, so interfaces become more important. Understanding the characteristics so important and what's happening there. So once you understand what's happening at the interfaces, then one can understand how it basically is switching the resistance in these devices. So in this work, what I did, I carried out ab initio calculations using density functional theory. So here I have a schematic of the device. So this is the side view. So you have gold, and then we have van der Waals gap in between the MoS2 and MoS2, and then you have again a van der Waals gap. So since the metal is symmetric, so there are 2 van der Waals gaps. And if you see a cross section here, which is shown here in the green, so you can see I have just shown one defect, and then there is this atomistic view of the same thing. So in this work, what I have done is, since most of the things, most interesting things happen around the defects, so what I have done, I have evaluated all the properties around the defect. So I observed based on electron density that the most changes happen within a radius of 4 nanometers. So a diameter of 4 angstroms. So a diameter of 8 angstroms was evaluated to understand the behavior of these. And one more important thing to understand is that here the convention I have taken is that a positive voltage is applied on the left electrode and the right is grounded. So the electrons will flow basically from right to left, which is the convention I will use in this work. In this experimental setup, it was the top and the bottom. The voltage was applied to the top electrode. So the convention is, it's very important to understand, the electrons will flow from right to left. So first what I did was, so I created these structures and then we optimized them. By optimization, I mean we put them in the lowest energy state, so then we can understand what's happening in the device. So 6 structures were studied. The first one here is the pristine. Then you can see here we have a single sulfur vacancy, then we have a disulfur vacancy, a molybdenum vacancy, and then 2 more cases where a gold atom was put at the monosulfur vacancy and disulfur vacancy. So the motivation for the last 2 cases was based on an experimental investigation which showed the importance that the gold atoms might be adsorbing there. So the next in the below, what you see is basically it's a superimposition of electron density onto these structures. So the red ones basically indicate electron accumulation. The blue ones indicate the regions where electrons basically deplete. Now from here, what I observed first was that how the gold is basically interacting with the sulfur of this MoS2. So for any 2 atoms to make a bond, the van der Waal radius, the bond length between them should be lesser than the van der Waal, less than the covalent distance. So if you see the covalent radius of sulfur and the gold, it's around 2.34 angstroms. But if you see the interfacial distances, they are more than that, around 2.5 angstroms. So which shows basically the nature of the contact here is of the van der Waal type. It's not making any covalent bond. But as you introduce defects into it, so you can see these things change. Because of the defects, there's a chemical interaction of the sulfur vacancy or disulfur vacancy or molybdenum vacancy with the gold. So basically the interaction changes, so the nature changes. And as you can see there, in the case where you have defects like a gold atom adsorbed at monosulfur and disulfur vacancy, the distance between the gold and the MoS2 drops to 1.93 and 1.74, which is less than the covalent radius. So it shows that in all the cases, in all the first 4 cases, the nature is still van der Waal, but when this thing happens, then there is a formation of like a conductive point link between these 2 now, the MoS2 and the gold. And we will see how it impacts the resistance to switching. So moving on next, like I said, I evaluated a radius of 4 angstroms around the defect to understand their behavior. So we calculated first the electron density, how it looks in the device. So we can see, so here are the insets that are there. So the insets basically show electron density at the interfaces, at these 2 interfaces. So, and the black one is basically a reference of the pristine. So we are seeing what happens when there are defects. So we see whenever we introduce a defect at one of the interfaces, you can see the electron density in all the defective cases increases, which means that defects basically enhance the chemical bonding at the interface, or they increase the reactivity at the interface. Except for 2 cases, which is once you have a sulfur vacancy or you have a gold atom adsorbed at sulfur vacancy. In that case, what happens is the electron density basically drops at the other interface. And in case of, you can also see a huge electron density here around at the interface. So this case corresponds to when you have a gold atom adsorbed at these monosulfur or disulfur vacancies as shown here. So you can also see here a red filament formation, which indicates there's a huge electron accumulation because of the adsorption of the gold atom. Then I also carried out electron localization to see how freely or how localized electrons are around the defects, and we observed that defects basically delocalize electrons. So you can see that except for the black case, which is a reference case, all these others have gone down. Less value of on this Y scale implies the electrons are more delocalized, and the higher value means they are more localized. So next, so far we understood that basically defects cause more reactivity at the or enhanced reactivity at the interface, and monosulfur vacancy basically degrades the quality of the other interface. Next, what is more important was to understand how barriers and quantum tunneling widths are affected because of these barriers. So I calculated what we call the effective potential. So you can see here. So this is the potential for the electron when it flows from one electrode to another electrode. So what kind of energy landscape it has to go through. Okay. So here I have shown these peaks for different kinds of atoms. So now what is important to understand here is, like I said, the electron travels from right to left because the positive voltage is applied at this electrode. So an electron will travel smoothly through the gold. Once it comes at the interface, it will face a bump. So this is what I call electron injection barrier from MoS2 into the, sorry, from gold into the MoS2. So that bump you can see here in the full potential, and it's shown here in the inset. And once it's inside the MoS2, then it has to come back from MoS2 and go into the another gold. So that's what I call an exit barrier. So there are two kinds of barriers. One it has to go into this and then come out of this. And what I observed from this is that the electron exit barrier is the highest out than the electron injection barrier. And once I calculated this, so you can see here that whenever you have a defect at one of these interfaces, at this interface, so what happens is basically the electron injection basically gets poor when you have a sulfur vacancy, monosulfur vacancy here. So this case here is the pristine, it is the reference case. So with the reference to this case, you can see monosulfur vacancy, the barrier, the injection barrier basically degrades, so the electron has to cross through a higher barrier. Same thing happens when you have a gold atom adsorbed at here. Same thing, but for other cases like where you have a disulfur vacancy, if you have a vacancy both here and here, the electron injection basically improves, and also for if you have a gold atom at a disulfur vacancy. And what happens to the exit barriers, which is these red ones? So for exit barriers, we see in all the cases the barriers keep on decreasing. But like I said, the exit barriers are very, very huge. If you see these two scales, so this one is very huge. And it's observed that only when a gold atom is adsorbed at the disulfur vacancy, there is a significant decrease in the barrier. So the electron initially, which had to tunnel through two barriers, now because of the gold atom, it provides an ohmic link, a kind of conductive point link between the two. So all the electrons will zap through it to another electrode. And same trend is observed with the tunneling widths as well. On the other side, now if you take a look at what's happening with the MoS2 when you put it between two metals. So if you see the DOS of MoS2, you can see it has a clean band gap. So there is this conduction band, you have valence band, and you have a band gap. But when you put MoS2 between two electrodes in this Atomristor configuration, what happens is we see there is a formation of mid-gap states. So this is also what's called metallization. So the MoS2 is like becoming kind of a pseudo metal. Now it has some metallized states. And this happens in all the cases. And when you have defects also, so it basically improves. So if you see, this is just the case of pristine, it has metallic states. And if you increase the defects, these kind of metallic states increase. So putting an MoS2 between gold electrodes, it first of all metallizes it. And then on top of that, what happens is the defects there will enhance this metallization more. So now to conclude, what's happening is, so you have this Atomristor, okay, in a high resistance state. So you have a disulfur vacancy. So the electrons will follow the tunneling path through this to MoS2 and then back to this. But once you apply voltage, positive voltage, so gold atom basically migrates, and when a positive voltage is applied to it, and because of that, the gold atoms from this gold electrode adsorb at the disulfur vacancies in this Atomristor, and because of that, what happens is this exit barrier drops very significantly compared to this one, and that's what basically then results in the low resistance state of this device. So it's like you have a metallic sheet, you have a metal, then you have a pseudo metal, then you have again a metal, and the transport is limited by how it moves across these van der Waals gaps. And when this gold atom gets adsorbed, it forms a link between these two, and that's how you get a high, so if you get a low resistance state in the device. That's it. Thank you.
Any questions?
Thank you.
But I have a lot of questions. I'll ask few for today. So first thing is, the one thing is DFT, right? So creating a defects in DFT because it's to oversimplify the model. Actually, when you create a fabricated device, you create this kind of deficiencies or defects are very difficult. Right? So how you overcome it?
So we generally choose a certain supercell size. So for instance, in this case, I choose a supercell size which gave me a defect density of 10 to the power 13 per centimeter square. So that was similar to what was used in the experiment, where they saw gold atom adsorption was probably the case. So I matched it with the experiment and then did it. Solution.
Okay, the second question is about this AU-MoS interface. It depends on a lot of conditions, right? It depends on temperature, surface roughness. So when you fabricate, how you take care of those things?
So like this is a computation work. So what I did here was, so the experiment.
Computation is fine. I have no question with it. Between I had which you answered earlier. When you come to fabrication, then all the things, game is all in fabrication. Right?
Yes.
So when you fabricate, that's a difficulty with the AU-MoS2 kind of interface when you create defects, right? That with temperature, with surface roughness, you may not get exactly what devices you compute while you're doing the DFT. So how will you take care of those
things in the experiment? So so while so what we can do is that we can intentionally create the defects into this. So we can use, like for instance, for these works, what people have done, they use e-beam to basically bombard the surface of the MoS2 before they deposit top metal. So by that you can generate, say for instance, you want to tune some parameters. So you can fabricate hundreds of these devices, use different kinds of e-beam dose, then optimize them to see what you want to get. So that's why you can understand that how much dose you need to apply for these materials to create what defect density is required for certain behavior to get this behavior.
Great. Last question. So when you do this resistive switching, right, continuously or repeated cycles, you will see that the defect would get into play.
Sorry?
When you do resistive switching for many cycles, the defects will get into play. That means that you will not have a similar kind of performance of the device.
Yes, so it will change. So there
in that case, how you take care of it?
So there is like cycle to cycle variability is an issue in these devices. That's why these devices are basically promise it as that they can improve that. Why? Because you see, when you have a thicker insulator, for instance, instead of this 3 layer, if you have thick oxide, so they're controlling these channels is very difficult at each cycle. But here, since the conduction is happening just because of one atom, so if you can properly engineer it, so then the variability will reduce. Although it will not be eliminated, but it will reduce, because you just need to only control how one atom is moving in and out of the sulfur vacancy. So by proper engineering of the defects into the device, what kind of defect density we require, then this can be reduced, but it cannot be eliminated.
Okay, great. Thank you.